So, and life behaves like a wave, right? And we know, there's physicists out there, they study the wave. So they know about the wave. What is a wave? Think about the wave like a cosine or a sine in your mathematics class. So what do we know about waves? We know a little bit about the mathematics of waves. What do we know in the math? What are, mathematics? What do we think about? Plus and minus. Things could add to. We could add numbers. We could subtract numbers in math. And when we talk about waves, how about if I have two waves? What they're going to do? Suppose I have two numbers in math. I could add them or I could subtract them. So waves work very similarly. I could add the waves together or I could subtract them. So when waves interact with one another, that's called interference. When they interfere with each other and then they add together, it's called constructive interference. When they interact with each other, again, interference, but when they interfere and they interfere in they subtract each other out, that's called destructive. So waves, they could, interact with each other. When they interact with each other, they could add or they could subtract each other out. So that's called constructive, destructive interference. That's like physics, math, right?
Would that
So
be the magnitude changing?
no, just uh, oh yeah, yes, constructive, yes, the magnitude. We're going to show that in the next slide. Yes, otherwise known as the amplitude. So let's take a look at this example. He is asking, he's one step ahead of us. So look at this wave here, and then this wave, and then it comes across another wave. But they both have the same wavelength. When they both have the same wavelength, they could interfere with one another. When they want to interfere with one another, what can they do? They can make the signal stronger. They could add, these two waves could add and make a bigger wave, but with the same wavelength. Same wavelength, but what's going to happen is what the person just mentioned. Oops, you could have a magnitude could be much higher. So a stronger signal, but the same wavelength. So that's called constructive interference. When the waves of the same wavelength, when they come together, they're going to add constructively. We call this in phase. Why is it in phase? Look at this peak and this peak, they're on the same phase. And what does that mean? Look at the one on the bottom. They both have the same wavelength, but here the peak is high and here the peak is low. So what happens when you add these things together? This might be a positive, this might be a negative. What happens when you add a positive and negative? They're going to cancel each other out. So this is called out of phase. So there are two waves, same wavelength, but they're out of phase. So think about like if you remember in math, cosine and sine, they're out of phase. So when these two waves come together, what's going to happen? Destructive interference. They cancel each other out. When this wave and this wave come together, what's the result? No wave. If I have no wave, then I have no light. So light behaves like a wave. And what do we know about the mathematics about waves? Mathematically, they could add or they could cancel each other out. So that's called constructive, destructive interference. So, and what do we know about waves? Now, this is not chemistry yet. This is still like physics, what they know about waves. Suppose look at the bottom one. Look at the bottom picture. Suppose if I throw a base, there's like a wall and there's a hole in the wall. If I throw a baseball through this hole, where's the baseball going to go? Straight, right? If I throw the baseball through this wall, is the baseball going to curve like this and go this way? No, it's going to go straight, and we call that a beam. Whenever things travel in a straight line and doesn't turn, it's a beam. Now we're going to do the same thing, but we're going to shoot some waves. Have a little hole in your wall, and then put some waves. And what's going to happen when it hits the wall? Of course, it's going to bounce back. But when it hits the opening, what we notice is when it hits the opening, the wave is going to spread out. So like when I'm talking to you right now, when I'm talking, I'm making a sound wave through my voice or whatever. So it's a wave. Can someone behind me hear what I'm talking? Or someone to the side of me hear what I'm saying? Yes, because when I'm speaking, the sound is going spreading out. So when a wave spreads out, we call that diffraction. So waves, they spread out. Just like if you drop a rock on, let's say, your bathtub or in a lake, what happens when you drop a rock in the water? The water is going to make these waves, and the waves are, what are the waves going to do? Spread out or stay in one spot? Spread out. So that's called diffraction. Waves diffract, they spread out. And a beam doesn't spread out, they just stay in a straight line. So waves, they spread out. That's what we know about waves, whether it be a sound wave, a light wave, ocean wave, waves spread out, diffract. So let's do this little experiment. So I'm going to get light. What do we about now? Light? We don't know, back then we don't know about light, so let's just do an experiment. Let's put a hole here. Let's put a hole here. And what's going to happen is this light is going to eventually go through that hole. And the same light is going to go through this hole. And what happens is, if light is a beam, all we're going to, and right here is a detector, a film. So whenever there's a black spot, no light. Whenever there's a white spot, light. So we could tell if light is hitting our detector in the back. If light was a beam, this light would just go straight and we see light here, light there, and nothing here in the middle. Because right, we have a wall blocking there. But what they notice is when they shoot light through this little hole, these two holes, we see light right here. How could light get there? It's right, there's no hole here. The wall's blocking that light. And that's just a simple experiment says light does spread out, diffract. Right? And then one other thing we notice is, okay, we got light here, but we got darkness here, darkness here. We got this pattern. Yes, no, yes, no. Why is there a yes, no pattern for this light? Why shouldn't they all have light because they're diffracting? And then light is spreading out. But what happened is you have light here on this hole, you have light on the other hole. Are these two waves of light going to hit each other? Bump into each other? Yes. When they bump into each other, that's called interference. When they interfere, what did we talk about last time? Last couple of slides. When they interfere, we could interfere constructively or, anyone remember? Destructively. So look at the bottom one right here. Let's look at this little bottom picture here. Where's my pen? Okay, there's a little bottom picture right there. So suppose this light is from this hole, and this light is from the bottom hole. When these two lights come together, they could add constructively, making a bigger wave with the same wavelength. Right? Or they could add destructively. So this light might be from this hole, this light might be from the bottom hole. They're in different phases, and when they come together, they're going to add destructively, resulting in a no wave. The waves cancel out. And when the waves cancel out, what happens? You get no light. You get dark spots. And you get this pattern of constructive, light, no light, light, no light. So that tells us light behaves like a wave, right? And we know the mathematics about a wave. They could add or they could subtract each other out. When they subtract, you get no light. When they add, you get light. So this is like a little experiment proving that point. Then they'll do this with different types of light. UV light, I don't know, microwave light, same pattern. Yes, no, yes, no, yes, no. But one thing you notice when you do different types of light, see this gap here, this distance? You're going to have a different distance or different gap. And then if you do some mathematics with that, then you could determine the wavelength of that light based on, this distance. And we're not going to get into that, but so this little experiment shows us light behaves like a wave. there's something called destructive constructive interference, and this gap distance is proportional to the wavelength. And if we do some fancy math, then we could calculate what is this wavelength of light, right? How do we know the wavelength of light? Do we have a ruler that can measure the wavelength of light? No. But we can measure this distance. We can measure how far this thing is from this wall, and we do some geometry, and then we can figure out what this wavelength of light is. All right, so that's called, so light. And what do we know about light? It behaves like a wave. And then what do we also know about light? Light has a wavelength, and that wavelength is related to energy. So this slide is just pretty much something called the photoelectric effect. I'm going to show you what that means in the next picture. What do you think photo means? Photo means like light, like photography is based on light, and where they get the word photos from photon, which means light. So light. And then what do you think electric means? Electricity. So if you look at this one here, this is a device. So if you focus on this one here, this little, so this is one electrode. This is another electrode. What happens is, I don't know if you guys did that conductivity lab here in this class, I'm not sure. So, but basically you hook up a battery and you put a little meter here. And if you connect these two pieces of metal, this thing's going to move. That means you're conducting electricity. But right here, these two metals are not touching each other, so that means no electricity is conducted because the air in between doesn't conduct electricity. But if I could get something to make these two metal things touch, this light bulb or this conducting meter will light up. So instead of having a conducting meter, we could have like a light bulb. Oops. If the light bulb lights up, that means electricity is flowing. If it doesn't light up, electricity is not flowing. So we put this in like a little glass tube like this, and we shine light on it. And why do we show light as like a little wave? Because light is a wave. We shine light on it. What happens? The electricity flows through this wire. How could electricity flow? These two metals have to touch each other. What happens when these two metals touch each other? Electrons flow from one metal to another metal. So when we shine light on it, electricity flows. How is that happening? Because if you look at this picture on the left, when light hits that metal, what is light? Light is energy, right? If I have the wavelength of light, I'm going to have energy. What happens if I put energy into something? So think about like a photon. Where's the electron in an atom? Out here. What happens if I put energy? Let me just draw this as an atom. Suppose this electron is it's held to the proton. There's some energy that's holding it together, right? Let's just assume the energy is 10 units. That's how strong this connection is. Electron to this proton is 10 units of energy. What happens if I put in 9 units of energy? Can I remove that electron? What do you think? Yes or no? Can I remove that electron with 9 units of energy? It's held down with 10 units of energy. What happens if I put in, oops. What happens if I put in 10 units of energy? Can I knock this electron off? Yes. How if I put in 11 units of energy? Can I knock that electron off? Yes, right? Because this proton electron is held down by 10 units, but if I put in 10 units or more, I can remove that electron. If I put in 10 units or less, I cannot remove that electron. So what happens when light hits this metal? That light has a certain amount of energy. Why? Because that light has a wavelength and has a certain amount of energy. When that atom absorb, when the light, the energy goes into the metal, if it has enough energy, the light has enough energy, what's going to happen to the electron? It's going to get knocked out. It's going to get removed from the proton or removed from the atom. So what's going to do, that electron is going to get out, it's going to jump off of this metal, and maybe it's going to move to this metal over here. So when the electron moves from one spot to the other spot, one metal to the other metal, that is called electricity. Right? You think it's a coincidence why we call these things electrons? And there's a word called electricity? Because what is electricity? The flow of electrons. When electrons move, that is electricity. So when these electrons are moving, flowing from one metal to another metal through this battery, oops, and then it's going to flow through this light bulb. And when electrons flow through that light bulb, the light bulb turns on. So this is called a photoelectric effect. Light is essentially creating or making electrons move. Anyone knows why this is important or not important?
Solar panels.
Can you say that louder?
Solar panels.
Solar panels. Right? That's how solar power works. Right? The light shines on your solar panel, and what happens? Something on your solar panel is releasing those light hits it. Electrons are coming off of that metal or that material, and it's going to be stored in a battery, or it's going to be used to turn on your light bulb at home, right? So the flow of electrons. So solar panels, yes. And to make, if you want to make a solar panel in which it's very difficult to remove the electron, or you want to make it so it's easy to remove that electron on a solar panel? You want it to be easy to remove that electron to come off. Right? So if I have a little bit of light outside, I'm going to still produce electricity. But if it's hard to remove this electron, then maybe the sun does not have enough energy to remove that electron. So we have to design these type of materials so the electrons could be removed with sunlight very easily. Right? So if you figure out how to make these materials, a good material, you pretty much you'd be a trillionaire, okay? Because everybody will have a solar panel at home or in their cars, and we don't need gasoline anymore. We're just gonna have all solar panels. If we could make a good solar panel. So this is called, so let's take a look at this one. There's a little picture on the bottom. We could shine light on something. When we shine light, we could shine it with a certain wavelength of light. This one has 700 nanometers. This is 550. So remember we said about the proton and electron. What happens? If I shine a certain amount of light on it, the electron doesn't fly off. Suppose suppose I put in 500. Let's just suppose I put in 550. See, I shine right here. I shine in 600 nanometers of light. The electron didn't fly off, didn't come off the atom. That means this light is not enough, does not have enough energy to remove that electron. What happens if I put in 551 nanometer? The electron did not come off. Why? Because I need to put in the right amount of energy to remove that electron. The electron is bounded to the center of the atom with a certain amount of energy, right? But then look, then I just keep on changing my wavelength of light, and then when I hit 550 nanometer, what happened? The electron came off. Why did the electron come off at 550 but not 551? Because 551 doesn't have enough energy. 550 does. So how strong is that electron connected to the center, to the atom? I'm going to put that 550 nanometers of light, put it into there. Do I know what h is? Yes. Do I know the speed of light? Yes. Do I know the wavelength of light needed to remove that electron? Yes. Now I just calculated the amount of energy that electron is, how strong that electron is connected to that atom. Right? Because I needed 550 nanometers to remove that electron. If it takes 550 nanometers of light to remove it, that's how much energy it is bounded to that atom. Right? So the amount of energy to remove it is the same energy is how it's bounded. So we know how much energy it takes to remove it. That amount of energy to remove it is how strong that electron is connected to the proton. And we could calculate that using this equation. Right?
In this scenario, it would be for a specific, say, atom that you're knocking off the molecule, or would it be like the fact that the nanometers are stronger as they go down?
Both, because we're going to talk about that. But all electrons are the same. But what depends on how strong this electron's bounded to the atom is based on its location. So think about like I have a staircase. Oops. I have an electron up there, A, electron down here, B. Which, and then this is the center. Okay. Which which electron is going to have more energy? Electron A or electron B? Think about which one's going to have more potential energy, A or B? A, right? But both these dots, they're the same electron. They're twin brothers. But what determines the energy of that electron? Based on its location. Every atom, these electrons are going to be slightly different location. If they're slightly different location, they're going to have a slightly different energy. So every atom, every molecule, it's going to be a slightly different amount of energy to remove that electron because every atom, these electrons are located slightly differently. And they're located slightly different location, they're going to have a different amount of energy. And we're going to get to those points next in this chapter. And again, this is a very important equation. If you know the wavelength, you know the energy. Okay? Then, I don't know, what was that saying? Anyone remember from their high school or elementary school? What is it? What is the sun made out of? Anyone know? What is the sun made out of?
Hydrogen?
Okay, hydrogen. How do you know that? Did somebody, an astronaut, go to the sun, collect the gas or collect the material from the sun, and then bring it back to Earth, and then we determine its sun is made out of hydrogen?
No.
No. So how do we determine that? So what happens is, I don't know if you ever know. I don't know. When I was a kid, I used to watch a lot of TV. So there's like this, medieval times. This guy's making a sword. When they make a sword, what do they do to the metal? They have to heat it up, right? When the metal gets really hot, what color is that metal?
Red or orange?
Why is metal red or orange when you heat it up? What happens is when you heat up anything, any element on a periodic table, if you heat it up hot enough, it's going to give off a color, give off light. So here, this little example here there's 3 different elements, and then if I heat it up, I get 3 different lights, red, pink, blue. So when you heat up anything, it's going to give off some light. And how do we know, how do we see that light? We see it with our eyes. But our eyes are pretty dumb. You can't tell us what's the nanometer, what's the wavelength of light. We just say, oh, it's blue, red, green. So we do this for different metals, sodium, potassium, lithium. We could do this for all the metals or everything on the periodic table. Sodium gives like, I don't know, orange, this one, whatever, purple, this one red, this one, I don't know, yellow. So all these elements give a different color, but some of them give very similar color, but our eyes are pretty dumb. We can't tell the difference, but you know, they all have a different, they release a certain amount of light. And what do we know about light? Light is a wavelength. So all these metals, when you heat it up, it gives off light. Why? Okay, why does this give off light? And why does it give off different colors of light? What do we know about different colors? Different colors means different wavelengths, right? And what we notice is now instead of using our eyes, we're going to use a special machine. And the special machine, we could tell what wavelength of light is coming out of that metal. So right here on the bottom is wavelength. And here's our metal, let's say sodium. When we heat up the sodium, it's going to release what type of light? Light at, I don't know, at this wavelength, light over here at this wavelength, light at this wavelength, light at this wavelength. Is there any light that's giving off right here at this wavelength?
Nope.
Nope. Every time there's a black spot, that means no light is being released from that atom. So, and what do we then? Okay, that's nice. This sodium. Let's look at hydrogen, calcium, mercury, and then they all give off light. But what happens? A different pattern, and also not just a different pattern, but different wavelengths, right? So we have a different pattern and we have different wavelengths. So we call this a fingerprint. Why do you think we call this a fingerprint? Does two people have the same fingerprint?
Nope.
Unique to that
Nope.
element.
Yep.
It's unique
That's right.
to that element. Yeah.
So there's how many elements are there in a periodic table? I don't know, 100, let's say 100 of them, 120, whatever. If I do this to all elements on a periodic table, I'm going to get a, are they all going to have the same pattern? Nope. They're all going to have a different pattern at different wavelengths, different number of lines, different wavelength, and now we have a fingerprint. Now instead of pointing our machine towards this little flame, let's point our machine to the, put it on a telescope, and let's point it towards the sun. And let's see what light is coming from the sun. And then the sun's going to give us a pattern, right? And we go, oh, the pattern we see from the sun is, one of the patterns we see is this pattern. Is that a coincidence? It matches up with hydrogen on Earth or helium on Earth? No. Then we go, oh, shoot. Right? So if the sun has the same pattern as hydrogen, the light that's coming out of the sun, that must mean the sun contains hydrogen. If it has the same pattern as helium, the sun contains helium. So that's how we know what the sun is made out of. We look at this little device, look at the sun, look at all the different wavelengths, look at the pattern, compare that pattern to all the elements we have on Earth, and it's a match with hydrogen, helium, a couple other things. So this is called a line spectrum emission. That means it's light is being coming out of the atom. So that is called the line spectrum, and this is used to identify all the elements, right? Has a nice pattern. And then how much hydrogen do we have? So if this line is thicker, more intense, then we have, that tells us how much we have. This pattern tells us what we have. But when this thing gets really intense, the light gets intense, that tells us how much we have. Right? So what can we use this for? Suppose, you know, how do you want to check if your drinking water is safe? How does the city check if there's any lead in your drinking water? They're going to get your drinking water, and what they're going to do, they're going to burn it. A really high temperature flame. Not just this weak temperature, it's going to be really super high. And what happens, whatever's in that water is going to give off light, right? Any element is going to give off light. So what we do, we get that water, heat it up really, really hot, break apart the water into individual atoms. So now we don't have H2O molecule anymore. We have hydrogen, oxygen, and whatever's in that water. And we break apart that water into high heat. And what happens when you have high heat? It's going to give off light. And then we look for something called, like, suppose we want to see any mercury in the water, then we look for this pattern in that water. If we don't see that pattern, no mercury. If we see this pattern, there's mercury. And then depending how bright this light is, will tell us how much mercury is in your water. So this is we use this technique to determine how pure, this is one technique to determine if your water has lead or mercury, or things like that. This is called through this emission. Because why? Because all elements have its own fingerprint. And then elements could release light, but what can elements also do? They can absorb light. So some elements, so this is the opposite. Every time you see a black line, that must mean the element is absorbing this light. Some elements absorb green light, some absorb red, blah, blah, blah. Right now I have a blue shirt. What does that mean? My shirt is absorbing all the light except blue. So all chemicals could absorb light. So this shirt this is a blue shirt, so it'll absorb all the light except blue. So only blue light's going to be bounced off my shirt, and that's what we see with our eyes. Right? If you go to the beach, what are you going to put on your skin? Butter or sunblock? What are you going to put on your
Sunblock.
skin?
Sunblock.
Why sunblock? Because there's some chemical in that sunblock that's going to absorb the UV light from the sun. Right? So some chemicals absorb UV light, some do not. So that's why we put sunblock on our skin when we go to the beach. Why don't we just put on water? No, water does not absorb UV light. But we put a chemical in that sunblock that absorbs UV light. Suppose UV light is like in this region here. I'm just going to say, so we have to make sure that your chemical is going to be all dark right here. It's going to absorb all the light in this region. So back here, a lot of slides we went through. Ultraviolet is in this region right here. This wavelength of light. So we have to design our sunblock, put the right chemical in there that's going to absorb this wavelength of light. So we have to design chemicals, test it, and if it absorbs this region of light, we're going to put that chemical into our sunblock. Right? So all the sunblock you buy, they all have the same chemical. This is no secret formula. We all know what absorbs. There's only like a handful of things we put in the sunblock. All the companies use the same chemical.
Is the chemical called SPF 50?
No, SPF 50 just says it's just there's you have a lot of that material. You have a lot of that chemical. So that means if you have a lot of the chemical, it's gonna last a longer time. So SPF 50, SPF 10, well 10 means maybe only gonna last me 10 minutes. Or SPF 50 might last me 50 minutes. So there's titanium oxide, it's one of the compounds. There's some other ones, but what's the difference between zinc? Yes. So what's the difference between all the sunblock is like sometimes I put sunblock, oh, it feels really oily on my skin. Or some, oh, it feels powdery. So that's the difference between all the sunblocks. They all have the same chemical, but the difference is some of them put different chemicals to make it feel better on your skin or smoother or whatever. But yeah, so we design the chemicals. We put them. One example is put them in sunblock. Why do we put them in sunblock? Because we know what wavelength of light they absorb. Right? So we want the sunblock to absorb the light, not your skin.
I wonder if in a couple centuries we'll look at that as barbaric as we did with like ladies using like lead-based makeup, because we're still like rubbing ourselves with metals. And I wonder if like later on we'll find out like, oh my God, humans just used to plaster themselves with this metal, similar to, you know, makeup.
Yep.
And all that.
Yep.
I guess we won't know, but later they'll know.
No, we know that now. Yes, this is sunblock.
Oh, sunblock is bad now?
There's two types of sunblock. I can't remember how they name it, but what you mentioned, titanium dioxide.
Yeah.
That's like a cover. You put it on and it's like acts like a film on your
Mhm.
skin. If you get the other type, that absorbs into your skin.
Oh,
But the one that absorbs into the skin, it feels better and it doesn't give you any white stuff on your face. So
uh-huh.
so the the zinc one is more healthier for you because it
Oh,
doesn't
good
get
to
it.
know.
Yeah, so it's like think about like a plastic, like a sheet on top of your skin.
Right.
But the other ones, they absorb into your skin, and so then that's problematic.
Right? That makes sense. Oh, wow. Yeah.
So if you get sunblock, get the zinc or the, even though it looks funny because you're gonna have this white thing on your face, but
Uh-huh.
that's the way to go. But you're absolutely correct, yes. Because what the sunblock people want to do, they want to make money, right?
Mhm.
And then worry about stuff later on.
You won't care. You'll be dead.
Yep.
Yeah.
So now you see this element, they have a pattern, right? Why does it have this pattern? Do these things have a wavelength, right? What are wavelengths? Wavelengths are numbers. And why is it at this point, not over here or over here? So then let's look at what is that pattern? Is there a pattern? Yes. Is this a random pattern? No, because every time I measure today, I measure tomorrow, I measure next year, it's always the same pattern. So there's a reason why it's in these locations. Now, is there a mathematical formula that I could make that could predict these wavelengths? So this guy Freiberg, came up with a math equation to predict this pattern for hydrogen. So what's that formula? 1 divided by the wavelength equals to some constant, 1 divided by n squared, 1 divided by n squared. And then they go, oh, and this n has to be 1, 2, 3, has to be an integer, whole number integer. Can't be 1.1, can't be 1.2, has to be 1, 2, 3, 4. And this equation predicts hydrogen. Not sodium, not calcium, only for hydrogen. Nobody's ever figured out a formula for the other elements. It's too complicated. But he figured out for hydrogen. So this one, this one, this one. How did he figure out? He came up with this equation. He doesn't know why it's true. He just knows mathematically this predicts it. And then, as scientists, we got to go, okay, there's some reason behind this. He predicted it. Okay, wavelength. Okay, that's what we're solving for. What is this n? N1, N2. Why it has to be whole numbers, right? So now this guy Borg comes along and comes up with this theory, says energy of an atom is quantized. That means the energy of an atom is related to the position of the electron. So where the electron is in an atom will determine the energy of that atom. So energy is quantized. What does quantized mean? Quantized means, let's go back to our staircase. Step 1, 2, 3, 4, 5. Where can my foot be? Step 1, step 2, step 3, step 4. Can my foot be at step 4.319? Or my foot could be at step 2.51? Yes or no?
No.
No. My foot could only be here, step 1, step 2, step 3. It can't be in between. And that's what quantized means. You could only be in specific spots. I cannot be halfway. I have to be here, yes or no, yes or no. So your foot, well, instead of saying my foot, now we're going to talk about the electron. The electron could only be in certain spots. So think about the Earth, or the sun, and then what's going around the sun? Planets, right? These planets are in orbits. If the planet's here, can the planet be right here? No, the planet has to be in its own orbit. There's another orbit here. Can the planet be like in between these two orbits? No. So these electrons are in these orbits, but they could only be in specific spots. Maybe the electron can be here and over here, but it cannot be in the middle. It could only be in its own lane, its own orbit. Just like a staircase, I could only be on step 1, 2, 3, 4, 5. I can't be at this one's orbit number 1, orbit number 2, orbit number 3. I cannot be at orbit 2.5. Same thing with steps. I could only be at 1, 2, 3, 4, 5. That's what quantized means. These electrons could only be in specific spots. If they're in specific spots, they could only have a specific amount of energy, right? So let's talk about the Bohr's model.
I have a quick question. So
Yep.
when we talk about the protons' positions and we learn how they fill their valence electrons fill shells a certain way, those electrons are in that certain position. That's the same thinking, like when we have whatever proton in the middle and then its electrons fill its valence shells. Is it following that same quantized law or no?
Yep.
Oh,
Yep.
okay.
We're going to get there later on in another hour. We'll be there. But yes,
Okay.
electrons could be only in certain positions. All electrons are the same, just depending on where it's located at. So when this orbit gets all filled up, it cannot hold any more electrons. Where's it going to go? The next ones, the next level. When this level gets filled up, where's the next level going? Where's the next electrons going to go? This level.
Oh, and that's crazy. It kind of does look like a fingerprint if you think about it.
Yeah. So we're going to get there. So this is a basic model. This is not what's actually happening for electrons.
Okay.
It's a little bit more complicated in this picture, but we're going to get there. Wait an hour. So Bohr comes up with this model that's saying these atoms have orbits, and electrons could be in these orbits. So think about my foot on the staircase, right here. Step 2. Where can I put my next step? Step 3. Maybe I put a little energy into my foot, into my leg. I could jump up to step number 4. Or maybe I'm strong. I could just skip 2 and 3. I could just jump to 5. So these, just like my leg could jump different steps, electrons could jump from one level to another level. How could electrons jump? How can my leg jump from one step to another step? I had to put energy into my leg. How could the electrons jump from one level to another level? I have to put energy into my electron. And what is energy? You think about heat. Right? If I put heat in, the electron's going to want to move around, and then has enough energy, it could jump. Could it jump like half a step? No, it only could jump and land on these orbits. It can't land in between orbits. So that's what this guy Bohr is saying. There's these orbits, and these electrons could move from orbit to orbit. So think about this. You have an electron over here. So now, let's say electron A, electron B. And I'm going to put in energy. All right. Which electrons is tighter to the center? A or B? A, right? So which one's more stable in terms of electron? Which electron you think is more stable? A or B? A, right? It's closer to the center, it's stable, connected. So if it's stable, you're going to have a high energy or low energy if it's stable? Low energy. So that means electron B is going to have a higher energy, right? Makes sense, right? A is more stable, low energy. B is less stable, it's farther away, higher energy. So now, these are all electrons. How does this electron jump up to here? I have to put energy in, right? Let's suppose this energy here is 10, and energy B here is 18. So I put enough energy, this electron from energy 10 went up to energy 18. Can you, when you're at home, can you watch TV for 5 hours standing up?
No.
Are you gonna watch TV standing up for
No.
5 hours?
No.
Could you watch TV standing up for like maybe like 10 minutes? Why would you sit down to watch TV? Does your body want to be at high energy or your body wants to be at low energy? Low energy. But if needed, I could stand up and watch TV for 30 minutes, right? I could put energy into my body and watch TV for 30 minutes, right? So electrons are the same thing. I put energy, what happens to the electron? It jumps up to here. But what's going to happen to this electron? It's going to get tired. And what's that electron going to do? Just like you're watching TV, it's going to want to sit back down, right? That electron's going to want to come back down. When it comes back down, I had an energy of 18. Now I have an energy of 10. How much energy did I lose when I sat back down, when I came back down?
8.
Where did that 8 units of energy go? Remember conservation of energy? I cannot create or destroy it. It had to go somewhere, right? So when we were up here, 18, now we're at 10, we lost 8 units. Where did that 8 units go?
Outside.
As light. It released that energy as light. So that's what this model is. When the electrons go from one orbit to another orbit, or higher energy to lower energy orbit, it releases energy and releases that energy as light. And that's how all light is produced. And what is E equals H? Do we have a little machine that could tell us the wavelength of light? We can measure the wavelength of light? Yes. So we're going to put a little machine here, and then we could measure this wavelength. Now we know the wavelength, now we know the energy. So now we can measure the energy of these orbits, the gap. Because when an electron comes from one orbit to another orbit, it's releasing light. We can measure that light. Now we know the energy difference between these orbits. And we notice that all atoms, they have a different gap. So right here we draw like this. Another atom could have oops, maybe I drew too similar. Another atom, the gap could be a lot smaller like this. They're all going to have orbits, but this gap is going to be different for every atom. When I have a different gap, I'm going to have a different wavelength of light. So if I have a different energy, I'm going to have a different wavelength of light. So you ever go to the store and you want to buy a light bulb and they said, oh, there's all these different type of light bulbs, daylight, yellow light bulb, red light bulb. How can I have these different colors of light? Because the material inside that light bulb has a different gap. And when the electrons come back down, it's going to release a different wavelength of light. Okay? So in your light bulb, you ever touched the light bulb before? Is your light bulb hot or cold?
Hot.
What is that heat going to do to this electron?
Release it.
Release
Make
it.
it, it's going to excite it and make this electron jump to another orbit. Are we talking about one electron or are we talking about Avogadro number of electrons?
Avogadro.
So you're going to get 100 trillion electrons going up, 100 trillion electrons coming down continuously. So that's why the light bulb is a little bit warm, because it has to make these electrons go up. And these electrons are going to eventually come back down continuously. And that's how light works. All light, any type of light, this is how it works. An electron going from one orbit, dropping down to another lower orbit. So let's do this in terms of energy. So where's your your lowest orbit, we call that the ground state. So I'm going to draw a little electron, draw it as a little arrow. So electron's right here. What happens when I put a little bit of energy into this atom? This electron's going to have some energy and it's going to jump. Maybe it's going to jump up there. Now the electron's excited, right? Just like you're watching TV standing up. You could watch TV standing up. You have some energy. You're excited. But eventually, what's going to happen? You're getting tired. And where's that electron going to go? It could come down here, or it could go down in one big step all the way down here. And when it comes down, what happens? I'm just going to make up a number. This is 18 units. This is 10 units. This is 16 units. If it goes down one step, how much energy do we lose going down one step?
+1 electron.
2.
2 units of energy. And we have a machine that can measure this. So when this light comes back down, it's going to release a photon, otherwise known as light. And we can measure this light. We know the wavelength of light. Now we can measure the energy. Now if we measure this light, now we know this. What is this energy difference from level 2 to level 1? Because we can measure this light.
I have a quick question.
Yep.
So the light is released. So there's ground state electron, energy is added. It excites the electron. When the electron loses energy is when it releases the photon, and we get light when it loses that energy.
Can you repeat the last step?
We excite the electron, it gets excited. Oh, and then when it loses energy, it releases a photon, we get light.
Yep.
Okay.
Because it loses energy. And what does it lose energy as?
Electrons. And when it releases electrons into the surroundings?
No, when it
It
loses
releases
energy.
photon.
Yeah, it releases that energy as light.
This is energy as light. Got it.
But there's different types of light, right? Depending on the wavelength.
Mm-hmm.
And how do we get a different wavelength? Depending on this gap. How big is the gap? It's jumping down. If it's jumping down a big gap, it's a short wavelength. If the gap is small, a long wavelength.
And that's our change in E.
Yep.
Okay. How much light is released is changed in E? One more time.
The wavelength of light.
Wavelength.
Okay. So that is how all light works. So look at this one here. We have our electron down here. Oops, where's my pen? Okay, down here. And when we heat up that electron, there's more than one orbit. There's like these atoms have many orbits. So when I heat it up, maybe it goes to level 5. But when from level 5, maybe it goes down to level 4. Or it could go from, remember, we're not talking about one electron, we're talking about Avogadro number, right? So maybe some of them is going to go down 1 level. Some of them is going to go down 2 levels. Some will go down 3. So every time you see this arrow going down, it's releasing light. So this one, how many different types of light are being released? 1, 2, 3, 4, 5, 6, 7, 8. There's 8. 8 times this electron's releasing light. And then in this gap from 5 to 3 is a different energy gap from 5 to 4. So there's a different energy gap. I'm going to have a different wavelength of light. So this is just one atom. So look at this. Hydrogen. Why is there 1, 2, 3, 4? Why is it releasing 4 different types of light? 4 different wavelength of light. Look at calcium. It's releasing, who knows, 20 of them. Why is it releasing different wavelengths? Because when an electron gets excited, it's going to jump up to here, but when it relaxes, when it comes back down, it could come back down in different pattern. Level 5 to 4, level 5 to 3, 5 to 1, 4-3, 4-1. When the electron comes down, every time it comes down, it's going to release a different wavelength of light. Every time it comes down, so it gives off a different wavelength, and so that explains why we have a different pattern. Why we have so many different wavelengths of light being released, and why does it have this pattern? The pattern depends on where the heck am I? So this pattern depends on this thing, level 1, 2, 3, 4, 5, and what is the gap? All atoms are going to have different gaps. Just like if you ever walk on a staircase, on some places, some staircases are very like this. Some staircases are very wide like this. Some are, so think about like all these atoms, they're going to have a different staircase. They're going to have the same number of steps, but the gap is going to be different for every staircase. And for every atom, these orbits, the distance or the energy difference between all these orbits are going to be different for every atom. And because this energy difference is different for every atom, when the electron moves from one orbit to another orbit, we're going to have a different E value. If we have a different E value, we're going to have a different wavelength. And if we have a different wavelength, we have a different type of light. So basically when electrons move from a higher energy to a lower energy, then that's when we have light. So that's why we need light bulbs. That's why we need to put in electricity into the light bulb to make the light bulb warm, hot. When you make those electrons hot, the electrons are going to get excited and they're going to jump to these other orbits. And when they come back down, they release light. So,
Sorry. Would
yep.
from 4 to 5 be dim and from 5 to 1 be bright?
Yes, let's examine this. 4 to 5. All right. Oh, this is HC, but we know C is a constant, H is a constant, so we're just going to say E is proportional to 1 over lambda. So 5 to 4, is that a small, and then what's the other one, 5 to 3 you said?
5 to 1.
5 to 1, okay, 5 to 1. So this is delta E. Which delta E is bigger?
5 to 1.
5 to 1, right? 5-1. This one's 5-4. So 5 to 1 has a bigger E. If I have a bigger E, what's going to happen to my wavelength? Smaller wavelength. The other situation, if I have a small, then my wavelength is going to be big. So the bigger energy gap difference, the smaller the wavelength. The smaller the energy gap, the bigger the wavelength. And we know that from before, right? When we talk about a short wavelength, more of these waves are going to hit you. And more of these waves hit you, you have a higher energy. So look at this one, answer this question, A, B, C, or D. BBB, yep, the lowest energy level for an electron is the ground state, yes. And then when it gets excited, it goes to something called the excited state. Then what we notice is, okay, now we understand how light works. Now let's do the same experiment with light, but let's just do it with electrons. So what we're going to do is do our double slit instead of having light here, we're going to put electrons. We're going to shoot electrons. And we're going to shoot electrons, and it's going to shoot them through this little slit here and this little slit here. And what we notice is we get this black, white, black, white, black, white pattern again. What does that mean? Anyone remember?
Interference.
Interference. What type of things have interference?
Like radio signals, so wavelengths.
Yep. Waves. So just based on this little experiment like this, electrons behave like what?
Waves.
Because of constructive and destructive interference. Only waves do constructive, destructive interference. So we go, oh, electrons behave like a wave. Right? Oh, that tells us a lot of information, right? Electrons behave like a wave. Why do they behave like a wave? Nobody really knows. But what we do know, anything that's really small like an electron, things that are like electrons, they all behave like a wave. They move like a wave. Things that are very, very, very small, like electron size, they move like a wave. Why? We don't know. Or no one really knows for sure. So again, this one's just a beam. What happens when you shoot a beam? We're just gonna shoot a beam through these two little holes. If I get a beam, the beam is gonna hit here, and the beam is gonna hit there. But no, electrons, they have a yes, no, yes, no, yes, no, yes, no pattern. It tells us electrons behave like a wave. So this guy de Broglie did this type of experiments and proved that electrons behave like a wave. So you say small things behave like a wave, have a character like a wave. And now we know the mathematics about waves, right? So what do we know about a wave? Like, have you ever been in an ocean and you see the wave? Does the wave stand still or is it constantly moving?
Constant.
Constantly moving. So waves, they're constantly moving. Do we know where it's at? At any electrons, they're so small. Can we see them with our eyes? We can't see them with our eyes. Do we have any tool to measure the electron? To tell us where the electron is? Not really. Electrons are just so small. But no, now we know they behave like a wave, right? Do we know the mathematics of waves? Yes. So now, where is that electron? Because the electron's constantly moving, so it has a velocity. So electron has a velocity and has a position. So if it's moving fast, that means I don't know where it's at because it's moving so fast. If it's moving really slow, then I can figure out where it's at because it's not moving. Right? So there's this relationship between velocity and position. So there's some mathematical relationship. We're not going to get involved into it, but the faster it goes, the less likely we know where it's at. The slower it goes, then we have a better idea where it's at. We don't know exactly, but we have a better idea. So in mathematics, we don't know. It's like you roll a dice. Do you know what you're going to roll before you roll the dice? Or if you flip a coin, you know what you're going to get before you flip the coin?
You just know the probability.
You know the probability. So waves, we don't know, it's always moving, so we don't know where it's at, but we could do some statistics. And when we do some statistics, high-level statistics, then we could figure out, okay, we could do the probability where the electron is going to be. Right? So we do like if you flip a coin, you don't know what you're going to get, but you can figure out the probability. So we can figure out what is the probability of the electron being over here. So, so we have to use mathematics, the statistics, to determine where is our electron. And if we do some high-level mathematics, and so this is like a probability. The more dots, the higher the probability of where the electron is going to be. So this is your center of your atom, and then go, oh, where we don't know where the electron is, but it has a high probability it's going to be in this circle shape. It could be over here, it could be here, like a sphere shape. So it's going to be inside the sphere. We don't know exactly because there's constantly moving, so it could be here, here, here. So the more dots represents higher probability. So we use a mathematical model saying, okay, electron is going to be in this region, and what we call that is an orbital. Space where you have a high probability of finding the electron. Because we don't know where the electron is, so we just call it an orbital, and that's where we think where the electron is going to be. So electron, like you think about planets, the planets travel in one direction on a line, in a circle. But electrons, they could be here, they could travel over here, travel over there, travel there, there, you know, who knows where it's going to be, right? It doesn't travel in a circle, it could travel, you know, like this anyway, right? But it's all going to be within this one sphere, and that is called an orbital. Probability of finding your electron. And we're not going to get into this high level. You probably need calculus in 3 dimensions to solve these type of equations. And then when we do this, we're finding the probability of finding the electron using the calculus and statistics. And that's called the Schrodinger equation. So we don't need calculus for this class, so we're not going to deal with that. But just think about it, statistics, finding the probability. And when we solve this complicated math equation, okay, so the premise is, the idea is electrons behave like a wave. And if it behaves like a wave, we don't know where it's at, so we have to make some assumptions, right? It behaves like a wave, blah, blah, blah. So we come up with this model. We don't know if this model is true or not, but we come up with mathematical equations. And then when we do these mathematical equations, we get 4 numbers, n, l, m sub l, m sub s. Okay, we don't really know what these numbers mean, but later on we're going to translate what they mean. So this mathematics gives us these 4 numbers, n, l, m sub l, m sub s. So when I get this number, L is going to be dependent on n. This number is going to be depending on L, whatever value we get for L. And we're going to talk about what that means pretty soon. So when we solve these equations, it gives us these 4 variables, 4 numbers. And out of these 4 numbers, we interpret them to mean certain things. And what the heck does that mean? So here's your nucleus or center. That's where your protons are. And we're going to have a layer. The first layer is called n equals to 1. Second layer, n equals to 2. Third layer, n equals to 3. So that's what n means. Which layer? So think about like an onion. In an onion, you have one layer, you have another layer, another layer. So these are layers. Can I have a layer 1.1 or 1.2? No, it's always going to be 1, 2, or 3. How do we know that? When we do the mathematics. N equals to 1, 2, or 3. Right? Just like the Rydberg equation. Remember the Rydberg equation? It's right here. Now we're figuring out what this n means. N means these layers. When an electron goes from one layer to another layer, then we can figure out what is that wavelength of light. So that's what the Rydberg equation means. From one layer to another layer, right? Because the electron has to travel from here. When it goes back down to here, it's an n equals to 2 to n equals to 1. That's what these n numbers mean here.
On that example, so it went from 2 to 1 and the other one had no movement?
So electrons have to move to give off light. So this might be like level number 1 here. Here level number 2. So this n and 1 might be, here would be 2, and this one would be 1. So 1 divided by 1, 1 divided by 1/2. So when light, to produce light, you always have to have movement of electrons from one layer to another layer. So that's what we figure out. What is this n? Mathematically, he just said these are n's, but later on we figure out, oh, this n values are these layers. N equals to 1, n equals to 2. If I have another layer, then it's n equals to 3. So that's where this, when we do the probability, okay, we got these layers. N equals 1, 2, 3. And then these layers have different energy, right? If you're closer to the nucleus, are you more stable or less stable if you're closer to the nucleus? What did we say?
More stable,
More
lower
stable.
energy.
If you're more stable, you're going to have a higher energy or lower energy?
Lower.
Lower. So n equals to 1. We're closer to the center. We have a more stable, so we're going to have a lower energy. N equals to 2, a little bit higher, 3. So now you got this level 1, 2, 3. They have a certain amount of energy. Right? How do we know the values of these energy? Because the electron is here, I could heat it up and make the electron go there. And then what's going to happen to the electron is going to come back down. When the electron comes back down, can I measure that with my instrument? Yes. Do I know the speed of light? Yes. Do I know h? Yes. Now I just calculated that delta E, the energy difference from here to here. Now I can measure these. I could start getting some values for these energy values. How much is what's the energy at level 1, level 2, level 3? Because I know when the electrons move, they're only going to move between orbits, and they're going to give up a certain wavelength of light, and the wavelength of light is equal to the, or once I have the wavelength of light, I can figure out the energies. So these levels 1, 2, 3, they have a certain amount of energy. So the closer you are to the center, the more stable you are, the lower the energy you have. Then they figure out, okay, is there some type of relationship between these levels? Some guy figured it out. This is part of the Rydberg equation. If you solve the Rydberg equation, you know, energy is this number divided by n squared. What is n? Level 1, level 2, level 3. So you could figure out what these numbers are through this equation right here. And then we could do it experimentally by just measuring the light that comes off of these electrons. And remember, let's suppose there's an electron right there, right? How do I know what the energy of the electron is? I'm going to hit enough, I'm going to put energy in here. And I'm going to remove this electron completely off of that atom. How much energy do I need to put in to remove that electron? Right here, that much energy. Remember the photoelectric effect? How much energy it takes to remove the electron completely? This much energy. So that's how we know level 1 is this much energy. All right, and then when we do our mathematics, we're not going to get into all the equations, but we just said n equals to 1, 2, 3, 4. Once we have n equals to 1, we can plug it into this equation. L is between 0 and n minus 1. And then once we have L, then we could figure out what is m sub L, because m sub L is going to be between minus L and plus L, and m sub S is going to be plus 1/2 or minus 1/2. So what we do first is figure out what is n, and then we figure out what is L, and then once we have L, we figure out what's m sub S. So we're going to get these numbers. So what n is, it tells us which layer we are. What layer are we in? We are level 1, level 2, level 3. Now, when we're inside level 1, we could have like a sub layer. There could be another layer inside that layer. So at level 1, I could have something inside that layer. Level 2, I could have something inside that layer. And level 3, I could have another sub layer. I know it's kind of confusing. So these are like our 3 levels. Think about N1, N2, N3. That's the distance away from the center. But when I'm at this distance away from the center, I could have some other things in there. And that's what we're going to talk about now. So what N tells us is how far, what shell we are, how far are we away from the center. L is going to tell us what is the shape of that orbital. What is an orbital again? Anyone remember?
It's the region where is the highest probability to find the electron.
Yep, probability of finding the electron. So it's going to have a shape. We're going to draw a shape. What the heck does that mean? Because over here, we're level 1. The probability of finding an electron at level 1 is going to have a certain orbital. Probability of finding an electron in level 2 is going to, it could be different from level 1. The probability of finding an electron at level 3, it could be different from level 2 or 3, or level 2 and 1. So this is going to show us, so what this means is, so when we find a, oops, what L is going to tell us when we solve for L, it's going to tell us the shape of the orbital. Why did this orbital have a shape? Because what's the probability of finding the electron? It's going to be inside this shape. And we call this one an S orbital. I'm guessing we call this an S orbital because it's a sphere. I'm not sure if that's the true meaning, but that's what I think about it. Sphere shape. Right? So the probability of finding an electron is in an S orbital. So when you do the mathematics, L equals to 0, we call that an S orbital. When L equals to 1, we call that a p orbital. What's the probability of finding an electron when L equals to 1? Propeller shape. So this is more like a propeller shape. It's not a sphere shape. The probability is finding it here and over here. Why does it have this shape? Mathematically, that's what it tells us. And then when L equals to 1, m's of L equals to, when L equals to 0, m's of L equals to 0. When L equals to 1, it's a p orbital, m's of L, it's hard to write, equals to 0, oops, minus 1, 0, plus 1. Look at this L. When L equals to 0, we have a S orbital. Look at the m's of L. M's of L equals to 0. M's of L on the bottom equals to 3 numbers. Look at this one. This is a d orbital. L equals to 2. M's of L equals to minus 2, minus 1, 0, plus 1, plus 2. 5. You see a pattern here? When m's of L equals 0, I have one of them. When m's of L is 3, I have 3 p orbitals. When m's of L is 5, I have 5 d orbitals. So this L value, 0, 1, and 2 tells us if I have an s orbital, p orbital, or a d orbital. This m's of L tells us how many orbitals do I have. This one I only have 1, I have 1 orbital. M's of L has three digits, so I have 3 p orbitals. D orbital has 5 digits, 1, 2, 3, 4, 5. So I have 5 d orbitals. Right? So this is just some theory someone had 50 years ago. Whether it's true or not, who knows back then, right? So they just come up with this theory, do this mathematics, try to interpret what do these numbers mean, and they come up, oh, L equals 0, that's the probability is, and then, we do some more calculus on it, and it tells us it's going to be a sphere shape. And then we could do some 3D calculus. When L equals to 1, we get 3 solutions, and then it gives us 3 p orbitals. When L equals to 2, we do the calculus, we call it d orbitals, we get 5 d orbitals. And why do these have the shape? Because that's the probability of finding an electron in these shapes. So just to clean it up a little, S orbital has this shape, a sphere shape. P orbital has a propeller shape. How many p orbitals are there? 3. D orbital, I don't know how to explain these shapes, but how many d orbitals are there? 5. So just during this mathematics, they don't know if it's right or wrong. They have to start from somewhere and come up with this model. We get this idea of these electrons are in this s orbital, p orbital, d orbitals. How many s orbitals are there? 1. How many p orbitals? 3. D orbitals? 5. Then the last number, m's of s. S means spin. And the numbers for m's of s can be plus 1/2 or minus 1/2. So what happens? Let's say, why does the Earth has a North Pole and a South Pole? The Moon doesn't have a North Pole or South Pole, but why does the Earth have a North Pole and a South Pole?
Rotating iron core.
What was that?
A rotating iron core.
Yeah, we have a magnetic field. And what makes a magnet? When you have electrons spinning. Oops. When an electron spins, I don't know what this direction is, counterclockwise, North Pole is down. When the electron's spinning clockwise, North Pole is up on a magnet. So these electrons have electron has a negative charge and they're spinning. That is a magnet. So when it spins one direction, we call that plus 1/2. When it spins the opposite direction, we call that minus 1/2. So on Earth has a magnetic field because in the center, there's like a river of iron, melted or liquid iron, and iron has a lot of electrons. And when they're spinning in one direction, like a river, and going clockwise or counterclockwise, that's why we have a North Pole and South Pole on Earth. The Moon doesn't have a North Pole or South Pole because the Moon in the center, there's nothing in the center. There's nothing moving around. So the Moon does not have a magnetic field. So the electrons could spin. When they spin one direction, plus 1/2, in the other direction, minus 1/2. So when I have a spin, we just show them as arrows. Spin up, spin down. So we show electrons as like an up arrow or a down arrow. So one thing we also figured out is in these orbits, how many electrons could be in an orbit? So this s orbital, if I have this s orbital, there's a probability of finding an electron, right? How many electrons could be in here? I could have 0, or I could have 1, or I could have 2. So there could be a maximum of 2 electrons in here. I could have 1, I could have 0, but maximum 2. So each one of these, how many can I have in here? 2, 2, 2. So p orbitals, I could have a maximum of 6. Because there could be 2 here, 2 here, 2 here. D orbital, I could have a maximum of 2, 2, 2, 2, 2, up to a maximum of 10. So every orbital could have a maximum of 2 electrons. I could have less than 2, but maximum of 2. So this situation, so how about if I have 2 electrons? That means one electron is going to be spinning up. How could the second electron be in the same, same one? Is the second electron be spinning up or the second one going to be spinning down? What do you think? Remember, electrons can spin, so we have one electron, let's say it's spinning up. The second electron, what's the value of the spinning up? It's going to be plus 1/2. How if another one goes spinning up? I'm going to have another plus 1/2. Do things want to be low energy or things want to be high energy? Low energy. So how can I get these 2 electrons to be in the same orbital but have a low energy? They're all going to be spinning the same direction or going to be spinning the opposite direction? Opposite direction. So if I have 2 electrons in the same orbital, they're going to be both spinning opposite direction. One spin up, one spin down. Because things want to be low energy. That's what this one says. If they're both going to be in the same orbit, they're going to be spinning opposite direction. So when L equals to 0, we have an s orbital. So instead of just saying L equals to 0, we just say s orbital. It makes our life easier, right? When we give things a name, it's easier to remember. S orbital, sphere shape. Okay? That's why you and I, we have a name instead of we have a number. Right? Instead of you being number 1 or number 2 or number 3, we give everyone a name. It's easier to remember. So this is an s orbital. L equals to 0 mathematically. S, you see that's an s orbital, sphere shape. Then we give it a number 1 in front. What the heck? No, it's an s orbital. Why did we put the number 1? So this is level 1, level 2. What we notice is there could be an s orbital here, level 1. There could be also an s orbital level 2 and s at level 3. How can I how do I know which one I'm talking about? The s orbital at level 1, 2, or 3? So what I have to do, sorry about that. I put a number 1 in front of here. This number 1 tells me I'm at shell number 1. I'm talking about the s orbital in shell number 1. That's what the number 1 in front means, 1s. Because that could also have a 2s orbital. That would be an s orbital in level number 2. So that's what the number 1 means. So you got level 1s, 2s, 3s. They're all going to have the same shape. But then the shape could be, if you're at level 1, maybe the shape is like this. But level 2, the shape could be still the same shape, but maybe it's going to be a bigger, I don't know, diameter, right? So they're all the same shape, but they're all going to be at different levels. I could have a 1s, 2s. How many electrons could be in the 1s? Anyone give me a number? How many electrons can be total in the 1s orbital? 2.
2.
How about the 3s? How many maximum? 2, yeah.
6.
Nope.
Oh, 3, 10.
2.
2.
How many electrons could be in an s orbital?
Oh, if it's the s orbital, it can only have up to 2, but it could have less. It could have like 1 or 2,
Yeah.
right?
The
Okay.
maximum 2. But the number in front just tells us which s orbital we're talking about. Am I talking about the s orbital in level 1, or the s orbital in level 2, or the s orbital in level 3? Level 1, 2, and 3, they're all going to have s orbitals. So how am I going to tell the difference between this one, this one, and this one? I got to put a number in the front. That's what these numbers here in the front means. This 1, 2, and 3, that means n. S means shape, n. Right? How many electrons could be in there? 2. How many there? 2. Here, 2. Maximum. What's the probability? They say there's you do the mathematics, 90% probability of finding an electron in this shape. Electrons could hold 2 electrons. If it holds 2 electrons, they're going to be opposite spin, right? One's going to be spin up, one's going to be spin down. L equals to 1, we call them p orbitals. And we do the mathematics and we solve for m's of L. We get this 3 numbers, -1, 0, and +1. What does that mean? We're just going to say that -1 equals to a p. This one's going to be another p orbital. This one's going to be another p orbital. So how many p orbitals we have? 3. And what is the shape of these p orbitals? Mathematically, this is the shape. There's 3 of them. Px, why do we call it Px, Py, Pz? Because it's along the x-axis, y-axis, z-axis. So there's 3 p orbitals. But in real life, we just separate them. Okay. So how many electrons could go in here maximum?
6.
Oh, this one by itself. 2. How about here? 2. That one here. 2. Then all together we have 6 because there's 3 p orbitals. And instead of we draw them individually like this because it's kind of easy to see. But in real life, they're going to be all combined. When they're all combined, they're going to look like this. And there's 3 p orbitals. And p orbitals, there's going to be a 2p, 3p, 4p. What does that 2 in the front mean? Level 2. At level 1, we don't have p orbitals. But level 2, we do. Level 3, we do. And why does it look like a propeller shape? That's what our mathematics tells us. That's the probability to find an electron in this region. Not over here, not over there, in this propeller shape. We have px, py, pz. And when we combine them all together, it kind of look like that. A lot of times we like to draw them individually. It's easier to see. And to show us there's 3 of them. In the d orbital, n equals to 2, we call them d orbitals. How many of these m's of L? 1, 2, 3, 4, 5. That tells us there's 5 d orbitals. How many electrons could go into this d orbital right here? Maximum. 2, right? Each one 2, but how many are there? 5 of them, so a total of 10. D orbitals. F orbitals, we're not going to get too much into F orbitals, but F orbitals, there's 1, 2, 3, 4, 5, 6, 7. So there's going to be 7 F orbitals. And those are the shape of the F orbitals. So in this class, we're going to focus on S, P, and D. If you do, this is a table with all the mathematics and all the numbers involved. You guys can look at that later.
SDPF, does that refer to the periodic table too?
Yes, we're going to get there. Yep. S, how many orbitals? 1. P, 3. D, 5. F, 7. Maximum number of electrons for each orbital? 2, 6, 10, 14, right? But each one holds 2 maximum. How are electrons going to fill up an atom? All electrons are the same. But what's going to happen is, oops, these orbitals, s orbital, p orbitals, they all have different energies. So if I have an electron and it's going to go into this atom, where's the electron going to go? Up here or down here? Where's the electron going to go? The lowest energy or the highest energy spot?
Lowest.
Lowest, right? Everything wants to be low energy. Oh, I got 1 electron here. How many electrons can this one hold, this 1s? Maximum.
2.
2. Put another electron there. How about if I have a second electron goes to go there? How about if I have a third electron? Where's it going to go? Can it go into here?
2s.
No, it can't go into there. It's full. So it's going to go the next lowest. And then where's the fourth side is full. And it's going to go up here. So there's a progression of how these electrons are located. So all atoms have this, all atoms have all these orbitals. They're just empty. Now, depending how many electrons you have, they're going to fill them up, lowest to highest. So all atoms have these orbitals. They're just empty. So if I have hydrogen, I only have 1 electron. But that hydrogen only has 1 electron, but it still has all these empty orbitals. What happens if I heat up this hydrogen? Where's that electron going to go? Maybe it'll go up here if I heat it up high enough. And what's going to happen to the electron when it starts losing energy? Maybe it'll come down here. maybe it come down here, or maybe it come down here. Every time the electron comes down, what does it do? It releases light.
Like,
But all atoms have these orbitals. They're just empty. But when they have more and more electrons, we start filling them up, based from lowest energy to highest energy.
so orbitals have something to do with an electron's potential energy too?
Yes, of course. Yep.
Okay.
Because where the electron's located at, the electron's going to have some energy. And here, electron located at the bottom is going to have low energy. Located on top is going to have higher energy. When it has higher energy, you think it could do something? Maybe it could do like a chemical reaction or something like that. Maybe it could do something. So, but we're going to get to there. You're ahead of us. So where is that electron located at? So we're going to do something called electron configuration. So this means 2p6. We have 6 electrons located at where? At the 2p. 2p is right here. How many electrons do we have? 1, 2, 3, 4, 5, 6. So that's what this electron configuration means. This number on top means how many electrons. P means which orbital. 2 means which shell are we talking about, which level. N equals to 1, N equals to 2. Which level, what shape, how many electrons. That's called electron configuration. So here for hydrogen, where are we? 1s1. How many electrons do we have? 1 electron. Then we're going to draw something called an orbital diagram. That's basically a box saying where is that 1 electron? We're just going to draw one arrow. Helium. What's the electron configuration? 1s2, because helium has 2 electrons. Where are those 2 electrons? At the 1s orbital. What is the electron? What is the orbital diagram? This one box represents that 1s. I'm going to draw an arrow up, arrow down. These 2 arrows means these 2 electrons. The electron orbital configuration tells us how are these electrons spinning. Can I have a 4th electron, a 3rd electron in here? No, because each orbital could only hold 2 electrons. So we do the same thing for lithium. Look at lithium on a periodic table, 3 electrons. If I have lithium, back over here, this is helium. Now I have a lithium. Lithium has 3 electrons. Where's the 3rd electron going to go? Right there. If I have beryllium, where's the next one going to go? Right there. So we're just going to go atom by atom and start filling this thing up based on this lowest energy to highest energy. Where's low energy? 1s, 2s, 2p. So there's an order in terms of lowest energy. How do we know this order? By doing this light experiment. So we get a pattern. Lithium, where's that 3rd electron going to go? To 2s. How about beryllium? Have 1 more electron. Where's that 1 more electron going to go? Oh, there's an empty spot there. So we got beryllium right there. 1s2, 2s2. How many total electrons does beryllium have? 4 electrons. 2 of them are going to be in this orbital, 2 of them are going to be in that orbital. The next one, what's after beryllium? Boron. 5 electrons. So here we have 4 electrons. They're all full. So where's the 5th electron going to go? To the 2p. It goes right there. 1s2, 2s2, 2p1. What's after boron? Carbon. Carbon has 1 more electron than boron. Where's the electron going to go? The electron could go there, but what happens is these 3 p orbitals, think about like in your home. If you have like 3 rooms in your home and you have a brother, are both of you going to go sleep in the same room? No, you want to spread out. So 1 electron is going to go there, 1 electron is going to go there. And when you're spread out, what happens is you're both swimming the same direction. That's what we find out experimentally. What's after carbon? Nitrogen. Now I got 3 p orbitals, 3 p electrons, but I got 3 rooms. So what's going to happen? These electrons are going to occupy 1 room each, 1 orbital each. Right? Because electrons, do they like each other? They're both negative charge, right? They don't want to be in the same room or same orbit unless they have to. If they have to, you have no choice, right? Now maybe you have a big family. Oxygen. You have 4 electrons, and these 4 electrons have to go in these 3 p orbitals. Now there's no other extra room, so that 4th electron has to share an orbital with one of the electrons. So what's oxygen? 1s2, 2s2, 2p4. And that 4 represents these 4 electrons there. Nitrogen, these 3 electrons represents these 3 electrons here. And what happens is these electrons are pointing all in the same direction, spinning the same direction if they're in different rooms. And so forth. You got this table in your book, so you know. We got the electron configuration. Electrons are filling up one by one. And then now right here, oh, shoot, this P, 2p6 is completely full. How about we have the next atom after neon? I think it's sodium. Where's that one more electron going to go? It can't go there. Now we're going to go to level 3. Right? This one's all full. Where's that one more electron going to go? Level 3. 1s2, 2p2, 2p6, 3s1. So I don't know if I have a picture of you. You have a periodic table to look at. Let's look at our periodic table here. On this one, hopefully you can see it. Oh, maybe this one I can't blow it up. Oh, this is great. I can't blow this one up. Yeah, maybe this one we can see it a little bit. Look at this. You see these numbers on the side? 1, 2, 3, 4, 5, 6, 7. Can you guys see that numbers? That's n. N equals to 1, n equals to 2. We're at layer number 1, layer number 2, layer number 3, layer number 4. Why does this table have this weird shape? Why do I have 2 columns here? Right? 1, 2. Look at this. Look at boron right here. 1 to neon. Count them. 1, 2, 3, 4, 5, 6. Okay. Look at the atoms here in the middle. SC. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2. You got 2 over here, 6 over here, 10 over here. You know how many we have down here? I'm guessing that's going to be 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. What does that relate to? Your p electrons, atoms are right here. 1, 2, 3, 4, 5, 6. P orbitals could hold a maximum of how many electrons? 6. S orbitals could hold a maximum of how many electrons? 2. 1, 2. D orbitals could hold a maximum of how many electrons for Ds? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this periodic table is designed, organized based on s orbitals, p electrons, d electrons. These are your s electrons. These are your p's. These are your d's. Down here are your f's. 14. So that's what we see. Sodium, 3s1. Why 3? Because now we're at level number 3. Look at sodium here. We're at row number 3. That number 3 means 3s. Right? And where's sodium on the periodic table? Right here. 3s1, 3s2. We're going to skip this. 2p1, or this is p1, p2, p3, p4, p5, p6. Here's d1, d2, d3. Right? So this periodic table is organized based on this s, p, and d orbitals. So which electrons do you think are important? The electrons in the center or the electrons on the outside? Let's see how many more slides we got. What do you guys think? Electrons in the center or the electrons on the outside? The electrons on the outside, and we call them the valence electrons. So in this case, how many valence electrons we have? Which are the outside electrons? Everything that's in layer number 3. What's in layer number 3? These 5 valence electrons. Right? These in the middle are going to be called the core electrons, core. Kind of an inside. But what do we care about? The valence electrons, the ones on our outside. Why? Because when one atom comes together with another atom, what's going to touch? The outside electrons or the inside electrons when two atoms come together? The outside electrons, right? So that's why we care about the outside electrons. And we give it a special name, valence electrons. All right. So this electron configuration corresponds to which atom? So we're running out of time, so we got to go a little bit quicker. So let's see, what time is it? Okay, we gotta. All right. So 1s2, 2p, 3s2, 3p6. So let's look at this. There's a couple ways to look at it. Okay. One way is to count the number of electrons. 2, 4, that's 6, that's 10, 18. All right. Which one on my periodic table here is 18? 18 is argon, right here. See argon? Another way, probably a better way of doing it. Look at this. 3s2, 3p6. Row 3, p6. What's on row 3 and has a 3p6? This one, argon. The answer is going to be C, argon. All right, why do we call this periodic table? Because a long time ago, oops, sorry about this. I think I just lost my pen. Can't write. So a long time ago, they called it a period. Same thing they call a row, they call it a period. And I think that's why they call it a periodic table. So period means a row. Right. And then the column, they call it a group. But now we just call them columns. So back then they call them group. So group 1, first column, they have a special name, call them alkali metals. Group 2, earth metals. Column 7, halogens. Column 8, noble gases. So these are the most common columns, which has a name. Oops. Column 1, alkali, alkaline. Column 7, halogens. Column 8, noble gases. The other ones have some names, but those are the common ones to know. Column 1, column 2, and the last 2 columns. First 2 columns, last 2 columns. So we talked about that before, right? You guys heard of alkali metals? Sometimes they use that in batteries. Column number 1, what they use in batteries? Lithium, right? Alkaline earth metals, right? You guys go and spend a lot of money and buy that alkaline water at the store. Alkaline water. What's in your alkaline water? Magnesium and calcium, otherwise known as tap water. Halogens, fluorine, chlorine, bromine. Noble gases, column rate, noble gases. Transition metals are also called, are these ones in the center here? D orbitals. transition metals right here in the middle. So these are your d orbitals. And these other ones, these are your f orbitals. We're not going to get too much into that, but basically transition metals you should be familiar with. These columns you should be familiar with. Now let's look at our periodic table. Let's
The F metals would have been like heavy metals.
F ones. They're way down here. These ones on the bottom, yeah, like uranium, plutonium, some of these down here. So in this class, we're not going to get into these, but we don't do too much chemistry in here unless you become like a nuclear scientist. Then we care about those. So now we're going to look at our periodic table, right? Hydrogen, lithium, sodium. This is the electron configuration. We're just writing down the valence electron configuration. 1s1, lithium, 2s1, sodium, 3s1. How many valence electrons in column number 1, these atoms? Give me a number. This pen is not working right now. See this number on top of that S? What's the number on top of that S?
1.
1. How many valence electrons we have?
1.
How about here, beryllium? What's the number on top?
2.
Magnesium?
Also 2.
2. Boron, how many valence electrons? 3. Yep, 2 plus 1. Yep. Aluminum, how many valence electrons?
3.
Do you see a pattern here?
The column is the valence electron.
Everything on the same column has the same number of valence electrons. So we organize it based on valence electrons too, this periodic table. Why? Because what does the chemistry? Inside electrons or outside electrons? Valence electrons. So if I have 3 valence electrons and this other atom has 3 valence electrons, I bet you they're going to have very similar chemistry. This other one has 4 valence electrons, another one has 4, they're going to have similar chemistry. So we organize this table based on number of valence electrons. So that's why we number this periodic table. This one's 1, 2. Then we skip the transition metals. We go 3, 4, 5, 6, 7, 8. What do you think these numbers on top mean? Column 1, 1 valence electron. Column 2, 2. Column 7, 7. Column 6, 6. This, we call this column 1, column 2. Then we'll come over here and call this one column number 3, 4, 5, 6, 7. So what does this column numbers mean? Number of valence electrons. Outermost electrons. So if you look at this periodic table, it kind of groups them. Here on the left, your s orbitals. Here on the right, your p orbitals. In the middle, d orbitals. Down here, f orbitals. So this table is designed on these valence electrons and the s, p, and d orbitals. Which ones are the core valence electrons? The outermost electrons, right? Level 1, level 2, or level 3? Oh, level 3. How many electrons do I have at level 3? 5. Since we only care about the valence electrons, sometimes we could do a shorthand. So see everything, the core electrons? 1s2, 2s2, 2p6. That's the same thing as neon. So sometimes we just write down the noble gas in brackets and then write down the valence electrons. So the top and bottom, they're the same thing. The bottom is shorthand. What can I do for abbreviations? The abbreviations could only be noble gases. They cannot be, you cannot put any other element. You only can put noble gases. Helium, neon, argon, krypton, and then the valence electrons. So this one, what is the electron configuration for this compound in the ground state? Ground state means I'm at the lowest energy level. That means I don't have any, my electrons are not excited. They're not moving around. This one, okay, look at neon, and then 1, 2p, 3p1. What element are we talking about? I'm talking about column number 3. You know, in column number 3, row number 3, because I got a 3. How many electrons do I have here? 3 electrons. So I'm looking at column number 3. What's column number 3 on the periodic table? Oops. Row number 3.
Aluminum?
1, 2. Aluminum. Right here. There's 3s, 3s2, 3p1. Aluminum. The answer should be aluminum. All right. And what's going on here? Here are these. This one's going to be aluminum. All right, put my pen back. So if you look at the periodic table, you know, we got metals, non-metals, metalloids. And what we notice is, let me see how many slides we have left. Oh, okay. Level 1, this is 1, 2, 3, 4. When we go down the periodic table, what's happening to the size of our elements? What's the radius of my element from the center to the outermost electron? What happens when I'm going level 2? Is my radius getting bigger or smaller?
Bigger.
What happens when I go level 3? Bigger, right? So when I go down the periodic table, my atom is getting bigger because when I go down, I'm going from different shells. My atom is getting bigger. Make sense? Now, when I'm going across this way, I'm in the same shell. I'm not going to the outer shell. I'm staying in this one shell. So my distance, my electrons are all kind of the same distance from the center. It's not going to a different shell, different level. But what's happening to my number of protons as I go from left to right? My number of protons are increasing. If my number of protons are increasing, that means the electrons are going to be held tighter to the center. If it's held tighter to the center, what's happening to my atom? Is it getting smaller? Yes, if I go from here, the atoms are going to start getting smaller and smaller because my electrons are going to get pulled in by more protons. So when I go down the periodic table, atoms are getting bigger. When I go across, it's getting smaller. So this just gives you the pattern, what's going on periodic table. Atoms are getting bigger. If I go this way, atoms are getting smaller. Because here I'm at the same level, level 1, level 2, level 3. If I go across, I'm not in a different level, so my electrons are not far away. They're all in the same area. But what happens is my number of protons are increasing. So the electrons are going to get closer and closer to the center of my atom. So this is a trend. Experimentally, this is what we see experimentally too when we measure it. Okay, ionization energy. What the heck does ionization mean? It means the amount of energy to remove the electron. When we remove the electron, what's easier to remove, the outside electron or the inside electron? What's easier to remove? Outside, right? So when I put in energy, the energy is going to remove the outside electron. So that's what ionization energy means. The amount of energy to remove the outermost electron. That's what this ionization means. So which is the outermost electron for the sodium? 3s1. So this is sodium, and I put in enough, and if I put in this much energy, that electron is going to fly off of that atom. When it flies off, what's left over? That 3s1 is gone, right? It's not there anymore because that got removed. So what's left over? This sodium plus is this electron configuration. So what is this electron configuration? 2p6. That is, I think that's neon, right? So you can have two different atoms have the same electron configuration, but this is sodium plus. So when we remove an electron, we're removing the outermost electron. So different atoms require different amount of energy to remove the electron, right? Because remember, where are these electrons in this s orbital, p orbitals, and they're going to have a different number of protons, and they're going to be held tightly, or they're going to be held loosely or tightly, certain distance away from the electron, different orbitals. So they're all going to require different amount of energy to remove that electron. What do you think is easier to remove? Which electron? Cesium or lithium? Which one's easier to remove an electron? Give me an answer. Cesium or lithium? Which one's easier to remove the electron?
Lithium.
Which one's easier to remove the electron? A or B? Why? Why B? Farther away. They're both valence electrons, but cesium is a bigger atom, so these electrons are farther away. If they're farther away in distance, they're not going to be held that tightly. They're loose. If they're loose, it's easy to remove it. So bigger the atom, easier to remove the electron. Right? That's why it's big, because the electrons are loose, they're far away. If they're tight, held tightly, they'll be very small. So it's easier to remove an electron as atom gets bigger. How about fluorine and lithium? Which one's easier to remove the electron?
Lithium.
Lithium's bigger, right? There's a reason why fluorine's really small, because the electrons are held really close, very tight to the center. Why is it held tight to the center? Because there's a strong attraction. Why is this atom bigger? Because there's a looser attraction for the electron to the proton. So when the atoms get smaller, it's harder to remove the electron. Atoms get bigger, easier to remove. So that's what this statement in the bottom says. You guys can read that. So now we have this, we could put in some energy. So this one, lithium to neon on the same row on the periodic table, we add energy. What happens? There's a general trend. It takes more energy to remove the electron as we go across the periodic table. And that's what we predicted. When atoms get smaller, they're going to get harder to remove. I need to put more energy to remove it. As I go down the periodic table, it takes less energy to remove that electron. So potassiums, I just need a little bit of energy. Hydrogen, I need a lot of energy. So this is matches up with the atom size. Smaller atoms, harder to remove electron. Bigger atoms, easier to remove. So you think it's easier to remove the first electron or the second electron? So there's first ionization, second ionization energy. So let me see how many more slides we got left. Okay. This is going to be a key point for the next semester. Next chapter. So what we notice here is hydrogen, it takes 2,000 units of energy to remove the energy from helium. Well, but lithium, 500 units. And then boron, carbon, neon, it takes 2,000 units. Why is that? Why did some of these take a lot of energy, some take a little bit of energy? So there's some atoms that they like electrons. They don't want to lose it. Some, I just put a little bit of energy and it loses it. Some, I have to put a lot of energy to lose it. What we notice, if you do this long enough, you look at column 1, 500. Sodium is also column 1. So we notice that atoms on column 1 It's easy to remove an electron. It takes a little bit of energy. Oops. But we notice so we see this pattern. So there's some atoms takes a lot of energy, some take a little bit of energy. If it takes a lot of energy to remove an electron, and one thing what we notice is helium, noble gas, neon, noble gas, and what we notice is things that are like noble gas, they are very inert. That means if I have do chemistry with noble gas, I put noble gas and I react it with some chemicals. Those noble gases don't react. They're pretty happy. So noble gases is very inert. They don't react with anything. And then what we notice is it takes a lot of energy to remove an electron from noble gases. That kind of tells us, maybe noble gases, they're happy with the number of electrons they have because they don't do any chemistry. They're happy. They don't need to do chemistry. They're happy. And then what we notice here is, look at this one, sodium. 500 units of energy to remove the first electron. How much energy to remove the second electron? 4,000 units. Why is a big difference? Why is there a big difference? Because look at the electron configuration for sodium.
So when it loses an electron, does it behave more like argon?
Yeah, we're going to get there. We're getting there, yes. So let me see if I have my periodic table. Sodium. Right. Now, when I remove that one electron, now this one is gone, right? What does this electron configuration look like? Look at my periodic table. Sodium -1 is neon. So now if I want to remove one of these electrons, that's my second one, I need to put in 4,000 units of energy. That tells us when I have something like a 2s2, 2p6, when I have this type of configuration, it's very hard to remove that electron. Why is it very hard to remove these 8 electrons? So there's this like magic number. Elements, they like to have 8 electrons. Why? We don't know. Maybe, these orbits are full. It's like you have a full stomach, you're hungry, you have a full stomach, you're happy. When you have 8 electrons, when these orbits are filled up, they're happy. When you're happy, you're stable. If you're stable, you don't want to lose any more electrons. So it takes a lot of energy to remove that electron. So we notice that noble gas configurations, they require a lot of energy to remove it. Why does it require a lot of energy? Because this type of 8 electrons is stable. And we're going to need that knowledge for the next chapter. So we see some trends on the periodic table. Non-metals. It takes a lot of energy to remove an electron. And non-metals, what we notice, they like to gain electrons. They don't like to lose electrons. They like to gain electrons. Since they like to gain electrons, they like to form anions. So we're going to talk more about this next chapter. So where are these non-metals? On the upper right-hand corner of the periodic table. These are your non-metals. And one theory is what's right after fluorine on the periodic table? Noble gas, right? These are your noble gases right here. How many valence electrons does fluorine have? Anyone know? What column is fluorine on the periodic table? Column number 7. Noble gases are column number 8. How many more electrons does fluorine need to become like a noble gas? It needs one more. So that's why fluorine is usually -1. How about oxygen? It has 6 valence electrons. How many more valence electrons does it need to get to noble gas?
2.
Oxygen is -2. So this is where we get this -1, -2 from, because atoms, they want to become like a noble gas. How can it become like a noble gas? It needs to gain one more electron. But look like an atom like sodium. How many more electrons does it need to become like a noble gas? It needs to, this is column 1. It needs to gain 7 more electrons. That's too much. You can't gain 7 more electrons. But what it could do is lose 1 electron to become like a noble gas. So things like sodium likes to lose. So metals like to lose based on where their location is. And then non-metals like to gain. Why does non-metals want to gain? Because they want to become like a noble gas. Metals like to lose to become like a noble gas. But how do they become noble gases? Metals have to lose it. Non-metals are pretty close to it, so they just gain it. So that's why a lot of metals react with a lot of non-metals. If this one wants to lose it, if this one loses it, who's going to gain it? The non-metal. So metals generally form ions. How do the metals generally form ions? Metals are usually going to become plus charges. They want to lose electrons to become like a noble gas. So which one of these are positive? These two are positive. How did this become positive? By gaining electrons or by losing electrons? Losing electrons. So let's take a break now. Let's see, what time is it right now? 10:20. So let's meet back at, let's take a long break today. 10:40 a.m. And so let's make sure you show back, because I think we might have a quiz. So make sure you come back at 10:40 a.m.